Okay, let's get started. Today, I want to introduce Dr. Tarditi, who's going to be giving a talk about plasma technologies and aerospace applications. And just give a little bit of background on Dr. Tarditi and on this talk. He's been working with UHCL for several years now. He started off as an adjunct here, and he's also worked with the Advanced Space Propulsion Lab when it was at JSC before it became Ad Astra. He has, he's also been appointed at UH Clear Lake as a research associate, which basically means he's been volunteering his time to help us build a plasma lab here on campus. And some of our students here have actually have worked with Dr. Tarditi on their capstone projects. And so a lot of his work is very interesting. He's got a background in electrical engineering, not physics, but you know, we're still okay with that. And a lot of the focus of his work has been on how do you use plasma physics for more engineering and more industrial applications. So I'll turn this over to Dr. Tarditi.
Welcome. I assume we have a very diverse audience, so I'm going to keep it a kind of a high-level style, and please do interrupt me anytime you wish. So don't wait the end of the talk and write down questions. This talk is designed to stimulate interest on plasma science topics that could be relevant for aerospace, whether you want to work in aerospace sector through NASA or you want to pursue your academic projects. There's space for everybody. That's why I'm basically highlighting NASA potential interest in plasma technologies, future and current, and the research potential we have here at UHCL, which is strongly dependent on the students, obviously, as usually is. We don't have a well-established research facility. We're just building things from scratch, basically. So what we're going to talk about here is what is a plasma, so everybody's on the same page, and then I will highlight some aerospace applications which are mainly research conducted across the country, outside the country, and see what we can do at UHCL. That's kind of the idea. The way I'm going to do this is to, what plasmas. So we will know what we're talking about. Most of you know what it is, or what plasmas are. And there's a pretty wide variety. And if you go on the web, you can find everything you want about just about any kind of plasmas. The main thing that you look at when plasmas are introduced are the density and temperature. And another thing is that usually people consider as a magnetic field. It's not essential, but it's very important oftentimes. But that just to give you an idea, plasma is just about everywhere. And as you probably know, the famous slogan that plasma physicists use to make sure that people think that they're actually important, that 99% of the matter in the universe is plasma. So you know, everybody should think about it. For the Earth, this is just an exception. So we're basically okay. This works to the pointer. That's good.
Not laser pointer?
No, I do have it, but I think it's easier for me to instead of going back and forth. Okay, so given this, you heard about the fourth state of matter. Why it's fourth and not, well, some people consider Bose-Einstein the fifth state of matter. I think it's fine. We can think of plasmas as a natural progression from solid to liquid to gas, and then there's something else, okay, which is still a gas, but it's usually hotter, and the density is usually it satisfies certain particular conditions. there's a difference between an ionized gas and a plasma. It may be just a matter of definition. If you read Chen's book, which is one of the most studied books in basic undergrad and grad courses, he likes to make a distinction between ionized gases and plasmas. Plasma is not a state of aggregation of matter, so it's not like it's any different from a gas for most intended purposes. But plasma is something else. It's something else because we can actually interact with plasma. We can interact with plasma with electromagnetic fields, and most gases do not respond well to magnetic fields with electromagnetic fields. The main features that are making a plasma different from an ionized gas is what is called quasi-neutrality and collective behavior. If you do understand this concept, then you do understand how to apply plasma physics and plasma technologies to more engineering-oriented problems like the one in aerospace that I'm describing. So, since this is a physics course, I'm going to touch on a little bit of physics. Okay, the main concept that you find everywhere about plasma physics when you start doing some quantitative assessments is the concept of Debye shielding. This is what the ionized gas may look like in a very, very crude approximation, with the blue being the electrons, the red being the ions, and the yellow being the neutrals. So everything is moving chaotically, and electric forces, of course, are playing main role here. Now, what happens if you stick a charge into this ionized gas, like this middle positive rod? Well, so the negative goes towards the positive, and the other one go away. But there is a distance at some point where this influence of the positive rod in the middle doesn't matter anymore, because there is enough electrons around that screen the effect of the positive charge. Well, you just discovered the concept of Debye shielding. If you go past that lambda d, it's called Debye length, you essentially see a neutral environment. It looks like exactly like your previous ionized gas. But in this region here, things are different. So when you can actually see a phenomenon of this kind, you're in presence of a shielding, and if the ionized gas allows you to see that, you can call it a plasma. If you don't have this happening because the gas is too rarefied or there are too many neutrals, and this is really not happening because collisions are dominant, then basically the whole plasma physics is close to useless. You're essentially dealing with the ionized gas, the single particle trajectory, not much more than that. So the whole knowledge of plasma physics, I wouldn't say rely on that, but it's heavily hinging on these simple concepts. Screening, the electrostatic screening that electrons, or in general charged particles, can go around any charge fluctuations. Of course, instead of being positive, it would be negative, it would be the other way around. So the Debye length is defined this way, and the only point of showing this formula is that you can see there's a temperature and a density dependence. So the temperature gets bigger, this lambda d gets a little bigger with a square root dependence. So you have a different kind of plasmas dependent on the temperature and density. This is what you see. So interstellar plasmas have density, very, very low densities, and temperatures are, well, unmeasured electron volts. You may or may not know that, but basically, 1 electron volt is about 11,000 Kelvin. And so you do the math, multiply by 10 to the 4, you get the temperature more or less. So you see the Debye length, this length that you have to screen this fluctuation of charges can vary a lot, from a meter to very small numbers. We are mainly interested in the ionosphere. You see that the Debye length is ordered of a millimeter. The other densities are related to more of astrophysics or space physics applications. In the labs, we can have usually we have densities in the order of a millimeter or centimeter. Reason being, our machines are not a kilometer long. They have to be, on the size of this room or smaller. So if you want to see something happening, and you want to call it a plasma, you have to have this debye length fairly small compared to the machine that you're running. I'm going to just skip on this. The concept of quasi-neutrality is another concept central to the plasma physics. Usually you see forces in ionized gases that are either Coulomb forces that go like 1 over r squared, or short-range interatomic potential or forces that go like 1 over r cubed or larger. In plasmas, there's these effects that are related to ions, to neutrals are not very important. So in plasmas, you only deal with this Coulomb forces. Very simple physics, we can say. There's not even much of a quantum physics that you really need. There are situations where quantum physics is relevant. Most of plasma physics is based on classical theories. So to get the bottom line, you can call an ionized gas, you can call it a plasma, if this lambda d, this shielding length is much smaller than capital L, where capital L is the size of your system, size of your machine, size of the domain you're studying, meaning there are many debye lengths, and so you can go away from this fluctuation of charge, and you can still see a neutrality in your system. And also the other condition that has to be verified is that these electric forces are the dominant players, and these collective effects, so-called collective effects, mean that you have a long-range force, an atom here all interacting with very small amount of atoms nearby, because this short-range force, but an electron or an ion, because the longer range of Coulomb force interact with all the particles away from it. And so in plasma, these collective effects are dominant, and this happens if this number, the density multiplied by a sphere, volume of a sphere of the radius of the debye length is much greater than 1. That means that there are many particles in a sphere of a radius of the debye length. So if a debye length is a meter, like in an interstellar plasma, we can call our system a plasma if we have a lot of particles in this meter sphere. And that means that the density has to be a certain number. If you are going into the lab, you have to have a little 1 millimeter or 1 centimeter debye length. So you have to have enough particles in this debye length and a little volume to call it plasma, because otherwise the fluctuations of particles that go in and out will mask in the whole collective effect or long-range terms that you have in your force interaction. There is something a little more than that related to collisions. If you read the textbook, we'll talk about. You also want to have. You call it plasma if, as I said, this long-range collective effects are dominant, and Coulomb forces are the dominant forces. If you are in a situation where there are a lot of collisions between ion electrons and neutrals, then the trajectory of a particle in the plasma will be affected mainly by the neutral and not by the charged particles. In this case, you really have a problem to define it as plasma. So the third condition would be that the number of collisions it has to be fairly small compared to some number that you define by the scale length of the Coulomb force. Anyway, without making the long story short, this is what I just said basically. And another thing that I haven't mentioned is that, and yeah, of course most people will be offended perhaps by this, but mainly, a lot of time, or mainly, we interact with plasmas with electromagnetic field. In particularly, studying magnetic fields have the nice property of confining plasmas. And the reason why they confine plasmas is because the force acting on the charged particles, if you remember, due to the magnetic field, is perpendicular to the velocity. And so if the particle wants to go up, the force goes to the left. So when the particle keeps going and right to the top, the particle keeps on being pulled down. It's like having a weight attached to a rope and turning around. Essentially, given a particle is confined around a circle. Yes?
That will confine it in the direction perpendicular to the magnetic field.
It's not.
But it won't confine it in the direction along the magnetic field.
You're correct.
Will it?
That's exactly right. And that's why we don't have fusion reactor right now, if you want to put it that way. People have been coming with very creative magnetic topologies to enclose this plasma and confine it no matter what. For example, taking the excellent point you made, because the particles are not confined along the magnetic field, if you imagine a straight magnetic field, you will have losses of particles along the field lines. However, if you take this magnetic field and you bend it and make a donut, okay, now there's no losses because the particles keep rotating in circles around the field, along the field lines. Okay, that's what all these toroidal machines, tokamaks and other concepts are based on. So yes, you confine the particle with that trick in the perpendicular direction, but you don't need to confine in the longitudinal direction simply because you bent the field line in a way that there is no way to escape it. In reality, the situation is a lot more complicated because when you consider, instead of single particle, you consider forces, collective forces on several particles, you see drift and other forces that are pushing the plasma away. And so confining even in these donut machines is pretty complicated, especially when the plasma gets really hot. So all these millions of dollars have been spent since 60s have been spent because it's so hard to confine plasmas when they get hot in this toroidal or other similar machines. Another concept that, I have it right here, as a matter of fact. Another concept, in fact, this was the first concept that was tried to confine particles in plasmas in magnetic fields, with magnetic fields, is what's called mirror. So the particles are not confined along the longitudinal direction simply because the forces are always perpendicular to their motion. However, if you make stronger the magnetic field in 2 points, the confinement in those 2 points becomes stronger than in the middle, and so some particles get reflected. That's why it's called magnetic mirror. Literally, they get reflected. If they try to get out, they bounce and come back. Well, not all of them. The ones that are really with the velocity along the axis, they do get out, but a lot come back. And so they build big machines based on this concept, hoping to get enough density and enough temperature to ignite fusion reactions. Some success has been made, but at some point the economics and maybe other political reasons drove this machine to their end, and so there's really not much done anymore in the simple concept. Plasma technology, fusion plasma technology, that has evolved in more complicated schemes presently. Sometimes somebody comes back with some revision of these simple schemes and some more creative ideas. Okay, now back to where we were about plasmas. We're going to talk about aerospace applications. This is my take on it. Probably forgot something, but that's what I'm going to entertain you on. You recognize some pictures and some concepts here. Essentially, we're going to talk about electric propulsion, which is not necessarily only plasma. In fact, electric propulsion started with ion engines, just ions. Basically ions and electrons separately. We're going to talk about the lunar environment, and the reason why we talk about that because there are a lot of electrostatic interesting charging effects that happens on the moon, in addition to what is called dusty plasma, which is a plasma which is more complex than just simple ions and electrons, but has macro particles, they're neutrals, but they get charged. The moon is a wonderful laboratory for dusty plasmas. If you want to save on a moon mission, you send dusty plasma physicists. They don't want to come back. You just want to stay there. You save the returns. Expensive. The moon actually. We've been there not too long, but we actually found some issues with the plasma dust, and I will talk about a little bit about when the astronauts were playing around the moon. Other applications are related to chemical / Mhd propulsion, which essentially it's a way to increase the performances of conventional chemical rockets, which are bound by intrinsic limitations of the propellant that we're using. The reason why it's so expensive to send stuff in orbit is because we have to use tons of propellant just to lift a rocket from the Earth. And there's not much that electric propulsion can do, because electric propulsion works well in space, where the thrust that you have to use to move a rocket is fairly small. The reason why that happens is because when you're sitting on Earth and you have a space shuttle on the ramp, the force that you need to lift that thing is huge. While you're up there in space, the gravity is much lower, and so you don't need as much force. Electric propulsion systems are intrinsically more efficient because they use less fuel to propel the spacecraft, but their capabilities in terms of thrust are limited by the amount of energy is available on board. And I will make this point a little more clear. So going back to the chemical Mhd propulsion, people have been trying to look at how can we improve the performance of the chemical rockets, and not just necessarily rockets, even high-altitude aircraft. For example, if you want to do supersonic or hypersonic flight for aircraft or missiles, missiles will have obviously defense applications. Hypersonic aircraft may in some future have civil applications, in the way that we've been thinking many times of having super fast aircraft that go from here to the opposite side of the Earth in a matter of minutes or hours, depending on how you go. So those studies were basically designed to have some kind of hybrid concept between plasma physics and a chemical rocket or a chemical engine to improve the performances. Plasma aerodynamics, that's an interesting field, and again, that has a lot of application for supersonic and hypersonic flights, although the picture you see there is actually a simple actuator, like a wing, showing an excellent attachment of the airflow on the side of the wing. If you're into aerodynamics, you will understand an attachment of the flow on the wing is very important to reduce the turbulence and the performance of the aircraft. The little purple stuff that you see is actually the plasma created on the surface of the wing, and because collision and attractive forces, the air gets attracted essentially along the wing. Otherwise, it would just go all over the place, and you will see the difference between plasma and no plasma. Lightning is, of course, a plasma phenomenon that happens on Earth all the time. We saw yesterday a lot of things happening here in the Seabrook area. For aerospace application, the reason why that is important is because our spacecraft and aircraft are oftentimes subject to lightning. They actually get hit, whether you're on the ramp or you're flying up. Up to, when you go above about 20 kilometers, there's no more lightning. But there are critical times of the flight when you're on the ramp, even when you transport the hardware from a cover station to the ramp, then when you recover your assets from space, while the craft is descending, lightning is a serious issue, more serious than many people think, and a lot of design effort has been put in making things more secure, safe. Plasma spacecraft interaction has been around for a while. That's a picture of the space station and sort of a potential map, and the different colors are showing you the different charging potentials that the space station is subject to. Because the plasma in space, the plasma is colliding with the surface of the space station, and some particles are collected, and the potential of the station with respect to plasma, the surrounding plasma in the atmosphere, becomes could be positive or negative depending on how things are set. On the station tends to be negative, and that could cause a hardship for astronauts that are flying around when they go outside on EVA. If they touch a surface that is 100 volts from the plasma where they are, they may be subjected to electrocution. There are other issues that are related to that, and basically related to how the materials are surviving for long term in space. Space station is a big experiment that we're making to do a lot of things. And among those, certainly a lot of information is coming on how hardware is surviving in space. And remember that the space station is not that far. It's the same distance from here to Dallas, except that it's vertical. It's about 400 kilometers, 250 miles or something. That is space, yes and no. I mean, it's in the atmosphere. Nothing compared to the moon, okay? The guys that went to the moon, well, guys were real astronauts. I mean, they went far. 384,000 kilometers average distance from the moon to the Earth. We're flying in space just 400 kilometers. The orders of magnitude less than the moon. So this is to say that we're really close to the Earth. We're inside the magnetosphere that's protecting us from a lot of bad stuff coming from the sun, from the cosmic rays. When we go out there and we travel to another celestial body like the moon or even further, problems are just getting worse. There's nothing gets better. And so material science is of paramount importance. If you want to really think about the emission to Mars with credible probability of success, meaning with humans, you want to take these people back and in good shape. Radiation protection becomes extremely important. Survival of materials in space due to radiation interaction with spacecraft becomes extremely important. And so the knowledge that we're gaining now, it's just the beginning. Of course, we send probes and automatic robots on Mars and other places, but usually we are not concerned about the survival of biologic tissue in those situations. We have, fairly robust metals and composite materials that can withstand a harsh environment. Space, for all intended purposes, is a harsh environment. It's probably one of the worst you can think of. Okay, I'm going to touch on some of these topics. 8 o'clock about finish. Most of you are familiar with the concept of electric propulsion. Picture is right here on purpose chosen to be Deep Space One, the first NASA craft that traveled far away out of the solar system and then was working on an ion engine, xenon ion engine. Very small craft, very small power. Was launched properly, and with some help of trajectory correction, it just made it all the way up, away from the solar system, collecting data beyond the expectations. The idea of electric propulsion is to try to go one step forward what we do now for chemical. And as I said before, rockets are intrinsically limited by the chemical reactions they use to propel themselves. We haven't found much better propellant than the beginning of rocket science. I mean, some improvement has been made, but nothing really. There's been no step change. We still use a lot of propellant, as I said before, to lift assets from the Earth, because we need thrust, and the only way to produce this thing is to burn this propellant and oxidizers. So we have to, in order to get some velocity out of this craft, we have to throw mass out, and there's not much you can do about it. Now, if you're thinking of, well, what if I throw the mass faster? I can maybe decrease the amount of mass that I can throw away, but I do it faster. I can get about the same result. Indeed, it's true. However, the speed of the ejection of the mass depends on the chemical reaction for chemical rockets, so you're stuck. Get whatever you get. The speed of the exhaust for chemical rockets is whatever it is. So the only way to go faster is to put more mass. It's like the car, okay? If you want to go faster with the car, you got to burn more gasoline. We haven't invented it. Well, I mean, aviation gas is a little more efficient, but how much? Okay, so the point being, you burn whatever you have, and you want to go faster, you got to burn more.
But isn't that mass per second rather than mass per se? I mean, you say mass, more mass. mass burned per second.
Well, right, of course.
Per
Slow,
second.
slow, yeah. In the same amount of time, you burn more mass. Yes.
I was going to clarify what you said. You burn more mass per second, that gives you a higher, what we call specific impulse.
A higher what?
But they're higher specific impulse.
Not with a chemical rock.
The specific, yeah, that relates to the exhaust velocity.
Right.
But there's still a limit on the total amount of mass in your tank.
Absolutely. That's.
So you could run
It all boils down to the rocket equation, okay? And so if this term here, the velocity of the exhaust gets larger, the amount of mass that you need gets smaller. But the velocity of the exhaust is determined by the chemical reaction. So unless you change the chemical reaction, there's nothing you can do about it. Or even instead of using chemical reaction, you do something else, okay? If you find a trick to increase the velocity of the exhaust, then you're fine. Then you can have a very fast exhaust, and then you don't have to get the same amount of delta V, get the same amount of acceleration of the craft in a time. You can decrease the mass. So the trick of electric propulsion is a way to accelerate propellant through electromagnetic fields. Propellant could be ions, could be something that responds to magnetic field. There's no intrinsic limitation in theory, because the more energy you put into this propellant, the faster it goes. While for chemical rockets, there's no way you can put more energy, because the energy is defined by the chemical reaction itself. So in principle, if you have a fusion reactor on board of your spacecraft, it will give you 100 gigawatts, you have a tremendous amount of energy available, and you can accelerate this fluid really fast. And so your rockets could potentially go at some reasonable fraction of the speed of the light. And so interstellar travel may become something conceivable. With chemical rockets, it's just ridiculous. Okay? You just can't do it. I mean, eventually something will get there, but we won't be here to do anything. So that's kind of the long-range attractiveness of this concept of electric propulsion. Practically, things are, of course, not always so simple. Basically, the trade-offs are that the more energy you have on board, the less propellant you can carry with you, because you can accelerate this propellant faster. That's great, because if you want to go to Mars, you only have to carry, a few hundred kilos or pounds of propellant instead of carrying tons. And the payload fraction can be much higher. That's just a win-win situation. The only point, you have to send this thing in orbit, because you can send stuff in orbit with the electric propulsion engine, but that's fine. You can have a shuttle-like rocket that sends all this stuff in orbit, and then from there you go with electric propulsion. That works perfectly. Also, if you have to send assets to the moon, like merchandise or anything that the astronauts can use, you can take your time. You don't have to go fast. You can have an automatic mission that goes to the moon, and it takes 30 days, for example. Okay, all it does is just spiraling around the Earth a little larger orbit, and then eventually reaches the moon. The delta V is very small. You can save a lot of propellant and be very efficient with electric propulsion. You can send a cargo to the moon or even further. And so when this material is ready, is arrived there, then you can send the astronaut faster, and they can catch up. So these are things that people have been dealing with. The concept of high specific impulse or high speed, as we just touched on it, in electric propulsion is much greater than in conventional rockets, and that makes the whole difference. So we have less propellant consumption. And another thing that we do consider in electric propulsion systems, the propulsion is continuous. Usually when you look at science fiction book or movie, we see a rocket in space, it's always a little plume out there. In reality, presently they don't. Okay, when we travel in space, we do a burn. We accelerate the craft towards the direction we want to go, and let it go, coast. Because there's nothing that slows the craft down. And then when we get close to where we're going to get, we correct a little bit because we may have missed something. So presently we do burns with our chemical rockets to achieve the delta V, the variation of velocity we want, and then we just coast. With electric propulsion, we can actually constantly accelerate because we don't use that much propellant, so we can be the most efficient we can by accelerating constantly up to the maximum speed that we need, and then we turn around and we decelerate when we get closer to destination. This way of traveling has also the advantage of creating a little bit of gravity, visual gravity, because you get an acceleration that, for all intent and purposes, will look like gravity to all who are on board. Well, there is a bunch of concepts that I'm going to go through. Some use ions or plasmas. Some use ions. Some use plasmas. The very first one is the ion engine that I described before. Essentially, you have a generator that produces some ions and plasma generator, if you like, ions and electrons not attached anymore, so it's a plasma or an ionized gas. And then you have a grid here with the potential, so the ions get accelerated and they leave the system. Well, they try to leave the system. In reality, they can't really leave the system too far, because if the ions wants to go too far and there's a bunch of electrons behind, the electric forces are pushing it back. So in order to make this thing work, we have to have an electron gun outside too. So what we're doing, we're accelerating the ions and we're releasing some electrons as well. So the total amount of charge that leaves the craft is balanced. Otherwise, it will never work. The ions are faster and massive, so even the electrons don't have too much energy. What happens is they get sort of attached and they travel with them. It happens in plasmas all the time. This is the way the Deep Space One engine looked. That's kind of the grid right in the middle. The ions go through that very fine grid. Performances. These are a little better engines in the kilowatt range that have been studied at JPL. Still, very efficient actually, and reliable, because the power. See, the power we're talking about here is kilowatt range. It's no big deal. Okay, we can have metals that sustain discharges and bombardment of ions, of currents that are necessary to create these kilowatts. The problem when you want to do a mission, human mission, and you need to carry a lot of mass, kilowatts don't go that far. You need more power to go somewhere, and that's why these engines have some kind of intrinsic limitation, because they're okay, they're good for essentially small power. The Hall thruster is another evolution of the ion engine, which essentially allows to be more efficient, and using the Hall effect, which is a simple physics effect that I had a slide before, just essentially improving the efficiency of the ion engine by collecting and injecting more ions, that you would otherwise. Still the same trick. You have to have an electron gun to get these electrons out. This is another picture of the Hall thruster. Essentially, you got these electrons that are spiralized, making a spiral around a coaxial structure, and the E forces and the electric field and the electric forces and the magnetic forces are perpendicular, creating a force on the ions and the electrons. Again, here we have a limited power range, kilowatt range. People have been thinking about in a matrix, an array of thrusters, and so you can actually have more power by making many of these engines. This is a magnetoplasma dynamic thruster, which is essentially using the J cross B effect. You have a current and a magnetic field that are perpendicular. There's a force in the direction of the perpendicular vector. It's the same as the Lorentz force, essentially, if you do a little bit of thinking about it. So these are two electrodes, a cathode and anode, and so you put a potential with a battery here, and you got a flow across this coaxial structure, and because the magnetic field is imposed and it's perpendicular to the current, you get a force towards this direction here. And so that's a plasma. So this is actually a plasma engine, not an ion engine. The plasma gets ejected, the whole electron and ion combo, not just the ions. It's called MPD. This is another concept that you probably heard about it. It's a Vasimir concept, which is a trademark of the Adastra Corporation, and there's going to be a talk about it, so I'm not going to discuss proprietary information. But basically, similar ideas have been used by attempting to increase the plasma injection and efficiency by heating the plasma and confining with a magnetic field. All these concepts use magnetic fields and radio frequency in different forms and combinations, try to do the trick. This is another concept from the Australian University, similar. This is basically borrowing from a very successful concept of plasma sources called helical sources that have been heavily used in the semiconductor industry. The semiconductor industry has a need of etching these large wafers of material, and so they have a plasma flow that hits the surface of the material. It's very important to have a very uniform plasma and control conditions, so they built these large plasma density sources, and they were very successful in doing so, and that's why the chips are one of the reasons why the chips are so cheap right now, because they have these machines that they can produce, on a wafer of this size. Okay, they produce 10,000 chips, all just in one shot. So this idea, this plasma generator, has been used for propulsion concept as well, and this is an experiment that was done in Switzerland, borrowing from the Australians in cooperation with the European Space Agency. Essentially, you have a large coil, and the plasma is created in the middle of the coil, and radio frequency is applied in a certain way to create modes that accelerate the plasma. It's a very rough summary of that. There's a lot more physics, obviously, behind that. The plasmoid thruster is something that I find particularly interesting because it's so connected to many other physics problems, fusion and astrophysics problem, or say space physics problem. The idea is that you create a little torus, okay, a little donut of plasma, and you inject it along the axis with magnetic fields. It's a little bit like a series of smoke rings. So instead of having a flow of plasma, you imagine you're just shooting a bunch of projectiles. You create this little torus, which is basically a donut-like shaped plasma that has its own magnetic field and current, and then you apply magnetic fields, external magnetic fields, and this torus accelerates. At some point, it gets injected. There are some advantages and disadvantages, but one main advantage is that these I'll touch on it later a little bit, but this torus, this bullet, the plasma, it's already detached, so to speak, from the main magnetic field. One problem of or some of this plasma concept is that if you create a plasma inside a magnetic field, the plasma tends to follow the magnetic field, as we touched at the very beginning. The particles are bound to these magnetic field lines. Okay, great. So I'm creating a plasma. The plasma is sitting on a magnetic field. The magnetic field is expanding. The line of forces are opening up. I want to make sure that this plasma leaves my rocket, leave my magnetic field. But in reality, physics tells me that the particles have to follow the lines. And so if it really things go as I think in a kind of naive way, they will follow the field lines, and then just go back and hit the rocket from the back. So on one hand, I'm throwing particle this way. On the other hand, I get particle from the other way, and I'll go nowhere. Okay, because the magnetic field always closes on itself. Okay, divergence of B is 0. Homework. What does that mean? What happened in reality is that non-ideal, non-single particle effects, collective effects, are responsible for creating conditions such that the particles have enough energy to detach from the magnetic field. And so you see these blobs of plasma that are leaving the magnetic field. This is now theory. This happens all the time on the sun. When we see solar flares or coronal mass ejections, these are humongous amount of plasmas that get ejected from the sun. The sun has a very strong magnetic field, a very strong magnetic field fluctuation. In fact, people have been studying the sun from a magnetic standpoint and try to understand what really happens, why these formations are able to stretch out of the sun. And if you look at the magnetic field inside these formations, you will see something like a little droplet of water that falls from the faucet. Okay, you see the droplet of water is formed, is still connected to the rest of the water in the faucet. But at some point, the weight and the size of the drop becomes big enough, the forces are able to detach this droplet of water from the remaining water, and so there is an empty space, and the water can fall down. Something like that happens with the plasma and the magnetic field, but not always. And the conditions why this occurs are not completely understood. This problem is called plasma detachment, or from an aerospace point of view, it's called reconnection from a plasma space science point of view. It's really the same thing. The magnetic field lines are perturbed or distorted until and stretch until they can't handle anymore, and then they break, they reconnect, so to speak. I have some pictures there. If we have time, I'm going to touch on. Okay, so to finish, electric propulsion applications are very appealing. Just for the ISS here on Earth, or near Earth, or for interplanetary mission, or for commercial defense, the way you like it, there are very appealing things. From a purely economical standpoint, I'll make this example to justify this kind of study. The ISS is falling from the sky all the time. You didn't know that? The space station is falling from the sky, so we have to reboost it. Because every time it goes around in orbit, it hits the atmosphere, plasma particles, and it slows down. If it slows down, it falls.
Isn't it supposed to be destroyed in 2015 anyway?
If you let it go. But personally, I believe it's just crazy to spend 20 years to build something, and then once you finish, you're done. Okay, I hope they keep on doing something. It happens all the time. I mean, it's really budget related, and I don't know. It's a political decision. Okay, since this is a free country where you can say whatever you want, reasonably speaking, I'll say that to me it's much better to go in space and keep asset in space than keep it asset in other countries, military assets. So we have to spend a lot more money in these adventures than space adventures. So I think we have the money. So it's just a matter of deciding to spend it. And one way to spend less money is to be more efficient when you're in space. You can use electric propulsion to reboost the station constantly, keep it in the same orbit that it is. Instead of sending propellant, the additional propellant on the shuttle or a Soyuz or automatic reboosting craft, they actually send more propellant just for the purpose of pushing the station higher. And the cost of that, estimated, and this actually was 5 years ago, it's tens of millions of dollars a year. Okay, just the weight of the additional fuel that you need to push this thing higher. So it's a lot of money that is just invested to keep this thing up, not just because of technology, just purely to keep it at the same altitude. The altitude really fluctuates. That what they do, they let it go down a little bit, and then the next flight they reboost it. Okay, so it goes up and down, which is really not good for like some microgravity experiments. You really would like to be perfectly at the same altitude all the time. Okay, let's see. We're getting close to the end. Let me touch on the UHCL side here. So, what you can do if you're interested in this kind of subjects here. Okay, of course, all these topics that I touch upon, not all of them, but touch them all. Many of these topics are studied extensively in different places. The Department of Defense is very interested in many applications of aerospace, obviously, of NASA and commercial sector as well. The current focus in terms of capabilities, whether it's computational, the more complicated things, of course, here can be done computationally, not on an experimental basis. We don't have tens of millions of dollars to invest in labs, but some simple things can be done too experimentally. We have some capabilities from a computational standpoint. For example, to study MHD, which means magneto hydrodynamic propulsion concepts, to study the concept of plasma actuator or plasma aerodynamics, how to design a plasma system that can cause the flow around a hypersonic aircraft to be deflected and to be more efficient from a turbulence standpoint. There could be a plasma simulation related to this concept of toroidal, small toroidal smoke ring-like configuration that you want to accelerate and inject. You have a question?
Yes, I'm
Sure.
curious on the electric propulsion line. What does the abbreviation FRC stand for?
Means field reverse configuration. The reason why it's here because I had a longer set of slides that would describe that. And essentially, the field reverse configuration, you'll see it in a second. It's one of those smoke ring-like configuration. It's a torus. We have invested a strong interest in lightning simulation. A simulation of the lightning channel can hit a spacecraft in different conditions. And there are profoundly interesting physics consideration that can be done and studied for magnetic reconnection and have application in both aerospace and space physics. I'm going to show you before moving to the next. Well, actually, I'm going to show the next slide. Simulation is somewhere that stays in between theory and experiment. Okay, so it helps both. We have capabilities to run Mhd, which is essentially like a fluidodynamic code with added magnetic field. Okay, a CFD, you have computational fluidodynamics. If you add the magnetic field, magnetic forces, you get into Mhd, Magneto hydrodynamic. Particle simulation, you simulate the motion of particles, ion electrons in force, electrostatic, electromagnetic forces. And all this is done in a massively parallel computing framework. I'm going to skip on that. This is what I was telling before about the FRC. This little smoke ring thing. Imagine a magnetic field, a simple dipolar magnetic field produced by some coil here. These are field lines. You perturb these field lines by injecting a current. Many ways you can do it. And then you stretch these field lines, and you keep on stretching it until it becomes detached from the main field. You are creating essentially a axisymmetric torus. So this little droplet of water in a axisymmetric configuration looks like a torus. It's exactly what this concept of FRC and accelerating this torus-like configuration is like. And this is essentially what plasma detachment may look like, as well as similar to solar ejection, solar mass injection, or even magnetospheric problem. This is a MHD magnetodynamic simulation of the same phenomena that was done a little while ago with a code that I actually work on. This is the FRC, field reverse configuration of plasma thruster. So you basically are creating this torus here from a plasma, and then you detach it and you accelerate it. You can do more than that. This is what some of the hardware that we have already. In fact, we have just about everything except the fact that we don't have two matching networks and the coils are not mounted. You can create it here in the lab. We have some activity in progress where we can create a plasma in the atmospheric environment, atmospheric pressure plasma. It's called plasma torch. I'm going to show you a little 1-second movie. Losing resolution if I go too fast. Okay, so the fluctuating light you see is the actual plasma coming from an argon ball. So the argon gets ionized, and then the radio frequency inside the coil is producing the plasma. The plasma is flowing through a glass tube and gets ionized. This is a torch in a very rudimental stage, but the good thing of this, although it's been built with not much effort, is that the original torches the original devices like these were using kilowatts of power. This was done with less than a kilowatt and not really well optimized. The point is that if we want to do aerospace application, you want to try to be very efficient. You don't want to carry kilowatt of power and wasting it all the way around. Okay, you want to use your power as much as better as you can. So back to our point to finish up. So this is the kind of activity that we can pursue in the lab. There's some planned activity which has to do with the vacuum chamber, which we don't have right now. This would be an example of what we would buy, sort of a long cylindrical shape where this smoke ring light can be accelerated, and that's for a different kind of application. Of course, it would be more like a plasma in the vacuum. Last thing I want to mention is fusion and plasma propulsion. They could be married together if you're conceiving a fusion reactor of some kind that is able to produce a flow plasma that gets out of the fusion reactor, and you accelerate this flow plasma if you need to, or you condition the flow plasma, goes through a nozzle and then exhaust it out. This simple concept was actually studied in different ways with this field reverse configuration in the past. So on one hand you have the rocket is exhausting, and the other hand essentially you're recycling whatever plasma gets out of here to produce energy with a direct conversion. I think I'm going to stop here and take some questions since it's long.
Okay, questions? Please.
Just a technicality here. Is it really important to separate plasma from ionized gas? Is there a sudden transition point or phase transition?
No, well, it is in a sense that if you don't know what the separation is, you may think you're going to see plasma-like phenomena, and you're not. For example, the concept of plasma sheath, which is related to the shielding effect, you can see near a surface. If you have particles bombarding a spacecraft in space, in the ionosphere, some of these particles get absorbed by the surface, and so the surface is charging up. And so there is going to be a non-neutral region near the spacecraft where there are more electrons and ions, or the other way around. If the condition of the placed plasma is, or the gas, or the ionized gas, is such that this thing is not really a plasma, the distance between the spacecraft that you have to travel to see a neutralization could be extremely high, and so you don't see a neutral environment as you would expect it, because you don't have enough space to neutralize this charge that can be absorbed. So if you want, it is in a sense a matter of definition. If you know what you're talking about, it's not a big deal. But the concept of the bi-length is a central concept. You always see the bi-length addressed when you talk about a certain kind of plasma, because it gives immediately a size of what you want to work with. So the bi-length is a meter, and your plasma device is a tenth of a meter. You don't have a plasma device, so you think you're gonna see some physics, you don't see anything. So that's why you want to know this kind of thing. Not really, it's not a formality. Oh, I saw you.
Yeah. My name's Alex Monchak. I'm taking this course as a continuing education student, and this course is about understanding scientific findings, new scientific findings, and possibly the publications.
Oh,
I was
okay.
wondering where would the research done at Clear Lake in this area be published, and where does JSC publish its advancements? Because you mentioned JSC.
The different, okay.
And just where did you find the publishing of those stuff that's already out there in this area?
Well, if you're looking for UHCL, like many universities, tend to publish on journals. Okay, so conferences, proceedings, and journals. Journals are better. Conference proceedings are faster and easier. So if you have something new, the idea is that you first want to go to a conference, get your paper published in the conference, and then you send it to a journal, so that the reviewers of the journal, when you see that your great idea, don't write an article themselves. That's really already published. So basically, that's the way the academic world works. Okay, journal publications are essentially the everything hinging on that. Okay, that's where you find things. JSC is a more complex environment because there's a lot of NASA report or or semi-official reports that get issued, regulation handbooks. There's a variety of publications. If you are inside the NASA environment, you have access to a very large database, the majority of which is online, which is extremely convenient. And so you see work has been done in the past that sometimes has not been published simply because people didn't have the time to do it, or it's been not so polished, or it's been maybe a limited scope. And so there is quite a large variety of publications. There's a lot of papers produced by NASA, but nowhere compared to the academic environment. So I'm not saying it's a little closed world, but the connection is not that simple. But a lot of stuff has been produced within the NASA. It's similar to DoD, okay? There's a lot of similar but not the same, because DoD has also a lot of non-classified publications that are reports, the Air Force Research Lab or Navy or Army labs. They don't make it to the journals because the people, maybe they don't have particular interest to publish on journals. It takes a little more time and more effort. They still have their job and they do fine without publication. But in the academia, if you don't have publication, you don't get your tenure. So that's pretty much the rule of the game.
Thank you.
Sure. Please.
Is there some more work that needs to be done on the interaction between these detached fields and that fairly well understood?
No, not at all. In fact, not at all. I would say it's an open problem, and people build their career on their conferences essentially dealing only with plasma recognition, specifically on plasma space science. So they're not even dealing with the specific of an aerospace application. They're talking about the magnetosphere and plasmas in the solar system that are going past and beyond the magnetosphere and how that behaves. There are some very important applications now that much more than used to be, and so this science, plasma science, space science becomes more an application science when you look from the space weather point of view. The space weather is a word to define the set of phenomena that is affecting the ionosphere coming from either the sun or the cosmic rays. And so the Earth is seeing certain space weather if you go outside the Earth atmosphere because the plasma coming from the sun. Fluctuations that occur on the sun are heavily affecting what happened on orbit. We have some striking examples, satellites basically being shut down by strong bursts of particles coming from the sun. So the study of these phenomena connected to the magnetosphere and the fluctuation of the magnetosphere itself and the fluctuation of the magnetic field on the sun are deeply connected with highly economically relevant applications. And so it's much more relevant today than it used to be. It used to be just a sort of a theoretical problem that people thought it was completely detached from the life. Now it isn't. Everybody's in a cell phone, and cell phone goes blank, the country stops.
Also, this propulsion technology, you can see a significant effect on performance based on...
Yes, indeed. That is, if you like, for right now, it's a smaller potato. I mean, if you talk to a telecommunication company and you say you find a way to predict, with a reasonable approximation, what the situation is going to be on the ionosphere given a certain sun fluctuation, then you get a job. I mean, a well-paid one, actually.
Just one question. You talked about fusion. This is a nuclear fusion?
Yeah.
Now, there's been a lot of problems with the toroid, I believe, over the years because of instability.
Problems, really?
Well, lots of them. Is this the analogy you gave where the water droplet from the tap sort of this is stability, part of the stability problem that we're dealing with?
You are correct. The stability of confined plasma is the main reason why we don't have fusion right now. Very stable plasma is being created, but the conditions were not close to the temperature and density we need to produce fusion. We got pretty close. We produced tens of megawatts of power in the machine in the UK, the JET, the Joint European Torus, as well as the Princeton Torus that was shut down now, as well as on the D3D in San Diego. However, we have not produced more energy than we consumed to reach those conditions. Lately, they also finish up somehow a laser-based fusion device in Livermore, California, which was also paid by the Department of Defense because they studied the implosion of small pellet of deuterium and tritium creating a plasma pushed by a bunch of lasers. They have 192 lasers. I actually have slides if you have time we can put to that. They can implode these pellets and they create essentially a small thermonuclear reaction, small thermonuclear bomb. So that from the DoD point of view, they can study on a small scale the physics of a thermonuclear blast. Some people question that it's really not that useful, but it's better than nothing because we don't have we don't blow bombs fortunately anymore. But anyway, it was good enough to get money from the DoD as well as from the Department of Energy to study this laser fusion concept, which has been done anyway in the past. But this is a different approach. It's called inertial confinement, where you literally push the sphere from all sides until it compresses and it gets so hot that you inject, you trigger the fusion reaction, and so this pellet implodes and then explodes. So what you do is just drop a pellet, blast it, drop another pellet, blast it. It's like a internal combustion engine in the car. Okay, you have cylinders and you have a discrete series of blasts. While the magnetic fusion is more like a aircraft turbine, where it keeps on rotating continuously. Okay, so we kind of give it.
Any other questions? All right, let's thank our speaker.